Morning. So, hope everybody's doing all right. Um, we're going to talk about work today. Uh, yeah, we'll see if we run into issues with the streaming quality again. It seems like we've had on two successive Mondays, we've had issues on Monday at 11 for whatever reason. So, we'll see if that happens. Hopefully, we can kind of just ride it through. But I appreciate your patience with the online stuff, and yeah, hopefully it goes smoothly today. We'll see. A couple of administrative issues that I wanted to mention before we get talking about actual physics. Let's see. So I'm swimming in grading stuff online, or I'm learning, getting at that too. So uh, I'm not going to give you a quiz on gravity or centripetal acceleration until at least the end of the week slash into next week because I want you to get feedback on all the stuff that you have out. So I'm working on that right now. Um, there were some questions about uh, quiz corrections showing up in the gradebook as a 0 and then that tanking the average. Um, so I think I fixed it in the gradebook, but I'm not in on Blackboard, but I'm not sure that it's going to stick. So watch that for me. I'm going to pay attention to it and see if we can if it stays. But it's has to do with that the gradebook in Blackboard and the gradebook in the homework system don't like play nice together. But I have the issue on my list of things to pay attention to, and so hopefully it's fixed now. But if it misbehaves again, I'll try some different things to get it straightened out. Um, let's see. That said, one thing I wanted to point out about the homework is that it's worth your while to complete homework assignments even after they're due, for a couple reasons. The primary reason being that it's practice, right? So it's good practice, um, and a great way to learn about the topics that we're talking about. But at the same time, you can also recoup almost all the credit for it. Um, if even if you turn it in after the deadline. So I would encourage folks, if you're, if you have a lot going on some week, come back to those homework assignments that you may have sort of tabled, and finish them. It'll help, with your understanding of the material, but also you can use it to increase your grade a little bit. Um, let's see. So I mentioned, yeah, gravity quiz probably in a week or so. That way too, if people have any questions about anything, if there's sort of if get lingering homework taken care of, etc. One main other sort of administrative issue that I wanted to talk about was the final. What we're going to do about the final. So thus far, it seems like it's worked okay to do quizzes rather than doing a midterm exam. And my rationale for that was just I didn't want to put that on you if it was not clear that it was going to work very well. So I think that's what we'll do for the rest of the quarter. We'll do smaller assessments, chunks, like these quizzes. And I feel like it kind of lowers the stakes of anything, if there are technical problems, if there are other issues with trying to do it online. But I would like to try and do something for a final that's more comprehensive. And it's going to be impossible to do a quiz that's comprehensive because it's just there's not enough substance. It wouldn't be long enough to cover, to give a good reflection of the different things that we've talked about in class. So I've been talking to other faculty about what they're doing, and there's some debate, among us about what's kind of the best way to go about this. But I think what we'll do is, since there's one leading idea would be to do it during lab time, or to do at least part of it during lab time. It seems to me to have worked fairly well to give you this where you have like a window, and then you have a timed quiz assessment during that window. But maybe we'll do something in conjunction with that for the final that's actually during the lab time. And yeah, that's what I'm leaning towards. But I wanted to bring that up to you now, so you kind of have it in the back of your mind. It seems like it's sort of a long ways away in one sense, but we're halfway through the quarter, so I want you to have a lot of notice as to any decisions that we're going to make about that. And that said, I want to get your input too. So one of the students or somebody mentioned in the morning in the 8 a.m. session maybe doing a survey. I think that would be a good idea. I can get some options developed and then ask you guys what you think would work best, and then we can kind of use that information to tailor what we'll do for the final. So those were the administrative issues that I wanted to mention. Things about grading, quizzes. If you see any issues in the gradebook or any other issues, let me know. I will keep those in the foreground and get them figured out. But sometimes they're kind of tricky to notice. Like there were some issues with the gradebook where almost all the grades for something were right, but a couple were screwed up for like a couple students. So if you're looking at that, let me know, and I will. It's not a problem. I'll get them tracked down. Any of these glitches and stuff, we're gonna fix it, right? We're gonna make it so that it errs in your favor, it goes in your direction. But I have to track them down. So let me know. Let's see. Does anybody have any questions about these sort of administrative issues? Let me switch back to. Nothing? You're all good? Ready to proceed? Okay, so let me know. Is everybody good? Yeah, we're good. Yeah, let me know in the chat how you're doing, and we'll get started here. Okay. So, oops. So work, it's like a lot of terms. It has, it has a lot of baggage. It has sort of a lay definition. We imagine, oh, we're doing work. Um, uh, so one of our goals for today is to give you the precise definition in terms of a physics context. I'll put it here. It's got a lot of baggage. What does it mean in physics? So the best way I think to show you this is by way of a picture here. So this is kind of a building on a simple type of system that we've dealt with before. Imagine you have a block. It has some mass or something. We're going to pull on it with some force. And we've done questions about this before where you could find, for example, the normal force. You could find the acceleration of the block using Newton's second law, etc. So the ingredient that we're going to add is now imagine that you have pulled this block through some distance. or technically, let's call this displacement. So I'll indicate this as a vector. So the definition of work is the force times the displacement times cosine theta. And actually, a more complete and correct definition of this is actually F dot D. So have you guys encountered this before, the dot product? So students this morning were saying that if they're in Calc 3 right now, they were seeing it maybe right now. Is that where you guys are at? It's totally fine if you haven't seen it too. We're gonna do some review because we kind of need everybody to be on the same page with this idea. So it's totally fine if you haven't encountered it yet. We're kind of doing it at the same time as those in Calc 3. So hopefully, one moment. Seems we're having technical issues. Is anybody having technical issues with the stream, or is it working out okay? One second, sorry. It's working? Okay. I just sent her a message. We'll see. Hopefully, maybe just a refresh or something will get that going. So, in any case, we were talking about the dot product. It sounds like a fair chunk of folks have been exposed to it before, or you're getting it right now. So, hopefully, this will work well. We'll spend a little bit of time reviewing because we want everybody to be on the same page. But it's a nice topic, or it's sort of a nice convergence of math and physics here because this gives us a real quantity to consider, a real thing to calculate with the dot product. So instead of it just being an abstract mathematical idea, which it is kind of an abstract mathematical idea, we have an actual application. And I suspect that in your math class, very likely you'll get problems that are calculate the work because work is calculated with the dot product. Okay, so we're gonna work on this today and tomorrow. One other thing I would mention, so the units for work, notice this will be units of forces in newtons. Our displacement would be in meters. So Newton meter, what is that exactly? Well, recall a Newton was a kilogram meter per second squared. And the unit of displacement, of course, would be meters. So this would be kilogram meters squared per second squared in base units. And this unit has the name joule. And this is the unit of energy. So this chapter and oh snap. The cosine theta. Where did the cosine theta go? So does cosine theta have any units? What is that? So this will be, the cosine piece is just a number. It won't have any units. So yeah, the units for work and energy, which we'll get into later in this chapter and in the next chapter, is joules. And something else I would point out, yeah, like I see in the chat, is mentioned that it's a scalar. Exactly. So this is kind of interesting. So work is a scalar. Well, I should say work energy is a scalar. It's an amount of something. It doesn't have direction. As opposed to, force. We've been talking about Newton's laws, forces. Direction was really a central idea with that, right? Your forces have direction associated with them. Forces are vectors. So another way to think about this is that let's see. So compared to forces, compared to displacement as well, actually. And this brings up. Let me kind of take an aside here, and we'll talk a little bit about math. So basically, there are three kinds of multiplication that we're going to encounter in this course. So the first one, whoops, we've already made use of, but we've sort of, we haven't called it anything. It doesn't really have a name. But that was the situation where, come on, pen. You have a scalar times a vector. And if you do this, you get a vector out. And the example that really comes to mind with this is Newton's second law. So if you look at both sides of this, mass was a scalar, acceleration is a vector. You multiply them together, you get force. Force is a vector. So this is an example of, well, here, why don't I write it just to be as I have it written up here. Scalar times vector gives you vector. It's the mass changes the size of that vector, but it does not change the it changes the it sets the size of the force, but it doesn't change the direction. So that's kind of what we've dealt with so far. We're now introducing a type of multiplication where we have a vector times a vector, and it gives a scalar. And this is the dot product. And the good example that we're working with now is work. And like we talked about up here, both the forces and the displacement are vectors, but the what you get out, the work and the energy, is a scalar. So vector, vector, scalar. And then the third kind is another kind of vector multiplication where you have a vector. Oh, and I should mention, if we're being careful, the symbol that we use to denote a dot product is a dot. So a lot of times we get kind of sloppy and use, like an X to represent multiplication, or you may have like two terms that are next to each other, or two variables that are next to each other, and they're multiplied together, in other words. And we don't use a symbol, so there is a little bit of ambiguity. But when we're talking about these various vector kinds of multiplication, I'll try and be careful and use the right symbol. So the other kind that we have is a vector times a vector, where we get a vector out. And the example that we'll eventually encounter on this is torque. And this will come later in the quarter, towards the end of the quarter. And this is called a cross product. Have you guys encountered that before or heard of that before, a cross product? And the symbol that we use to denote that is like a big cross, X. So some have. I suspect most of you have not. Where did you guys run into that before, the cross product? Yeah, it's totally fine if you haven't encountered that yet. Ah, you see it in Calc 3. Okay, cool. So we're not going to see it quite yet. More towards the end of the quarter, hopefully. We'll have some time for it. It comes up in, like I said, with regards to torque. The you'll learn in Calc the procedure for how you calculate it. But yeah, it's totally fine if you haven't encountered that one. We'll come back to this and how to do those, find cross products later. But we will talk in a little more detail today / tomorrow or / Wednesday about calculating. Yeah, exactly. So that's a good way to sum it up, actually, is to say, in other words, a vector dot vector does not give you the same thing as a vector cross a vector. These are different operations. And kind of a similar thing would be to say, like v1, v2, if these are vectors, this is kind of ambiguous. Like, is this a cross product? Is it a dot product? Like, you don't know. So, like I said, and it's just not a well-formed statement. So, if we are going to multiply vectors, we'll use either the cross or the dot. Okay. That's not confusing at all. No, it is confusing. It is confusing. Um, uh, you know, it's confusing in isolation, especially. But I think you'll find that when you see it sort of in context, it's going to be clear which kind of product you're talking about, because you will know, for example, like, well, we're calculating work. We know that work is the dot product. It's not going to be appropriate to get out something that's a vector, for example, because you know that it should yield something that is just a scalar, that's just energy. So yeah, it's kind of I agree. It is a little bit confusing when it's in isolation like that, but it'll be all right. Okay, so let me give you some simple examples of work. So the first example that I want you to think about is, actually, let me show you on video here for a second. I think it's useful for you to kind of see this and to manipulate an object yourself so you can get a sense for what I mean. And that is, so imagine you have like a coffee cup, and the first example, let me try and center this here, that I want you to think about is if you're holding the coffee cup. So there is a force of gravity that's pointing down, and there's the force that you're exerting on the cup that's holding it up. But I'm just holding it here. It's not moving. So in that situation, the work that's being done that you're doing on this coffee cup is 0 because the displacement is 0. Okay? Now, a very similar example. If I take this coffee cup, the force that I'm exerting on it is pointed up. The force of gravity is pointing down. And then I move it. If I translate it, the displacement in this case is sideways, but the force is pointed up. So in this situation, the work is also 0 because the force and the displacement are perpendicular to each other, and F, throw it, F dot D will be 0 because cosine of 90 degrees will give you 0. Okay, so the third kind of simple situation to consider would be, okay, you have your mug. Now, if I lift it up, okay, if I'm pushing it up, lifting it, now, and assume that the speed that we're moving it with, the velocity is more or less constant. In that situation, you are doing positive work on it because the displacement and the force that you're exerting on it are in the same direction. So, and the one caveat that I would mention with this example is we're thinking about it in the sort of idealized situation where the cup is moving at a constant velocity. If it's accelerating, that's a different story. So we're not considering that situation. But as you can see, I mean, that's only it's only like right at the beginning of the motion and right at the end. While it's moving at a constant velocity, then it would just be regular work. Let me switch back to my screen and let me kind of sketch out to you what I just showed you. So, alas, I won't throw my mug. I need my coffee. So I think, and you can kind of think about this. You can grab something, whatever's handy, and kind of think about the same example. So in this, the first example, let me sketch this here. So the first example, we were just holding it. So in this situation, the force that you're exerting on it is pointing up. The weight of the mug is pointing down. And the work is 0 because F d cosine theta, the d was 0. There was no displacement. Okay. So that's kind of the trivial, sort of the 0 case. So the next example that I was showing you was, okay, what if instead of just holding it, you actually translate it. Now, in this case, the work is also 0, but this is for a different reason. This is because F d cosine theta, well, if the displacement and the force are perpendicular, then this would be 90 degrees, i.e. F d cosine of 90 degrees. That is 0. So then this would be 0. Okay. And then kind of the other example that I was showing you is, okay, so what if, actually, let me give myself a little more room here. What if instead we imagine lifting, oh man. if we lift it up, it's the same situation. The force is still down. The force that we're exerting on it, I'm calling the holding force, is pointed up. But now the displacement vector is in the same direction. And in this case, the work is not going to be 0. Actually, let me say it in words first. So, and this is an excellent question. Is there not a lateral force to make it move? There is, and the thing is we're assuming that this is just the case where it's moving at a constant velocity, in which case the lateral force would, the sum of the lateral forces during that time would be 0, okay? So if we were to look at the situation where it accelerates, then that would be a different story. So yeah, that's an excellent question. So let me just put this as we're assuming constant velocity, i.e. not accelerating. So, but then, you know, the natural next question with this would be, well, what exactly is the magnitude of the work? And to do that, we have to look at the forces. So if we look at the forces in y, while it's moving at constant v, so let me just say, you know, at constant v, in that situation, the forces that we have our holding force that's pointed up. We're going to have the object's weight that's pointed down, and those are going to sum to 0 when there's no acceleration. And as a result, we can calculate we can solve for what the size of the holding force is, and it's the same as the object's weight. So then when we go to calculate the work, if they're parallel, this is the same. This becomes FD cosine of 0. So this becomes 1, in other words. And so the force that we had was mg, and the displacement was, you know, however far we move it, so it would become just mgd. Okay. Questions on that so far? So that's kind of the base example. There's one. Wait, 1 second here. Here, I'll show you guys. Maybe your other classes have been having guest appearances, but my wife is in a meeting right now, and so I have the dog in the room that I'm trying to do class in, and she is causing trouble. But here, you guys can meet her. So this is Rory. She's kind of an assistant / kind of just being a troublemaker and trying to eat like the post-it notes and stuff that I have for things that we need to do. So if you hear some rustling around and stuff, that's what's causing it. She may appear in some questions. She's busily eating my scrap paper right now. So do you guys have any questions so far about work? Yeah, I'll have to work her into some example problems. She alternates between being totally chill and just causing a fair amount of trouble, and she's trying to cause some trouble right now. No. Uh, okay, so the other thing that I want to show you about this example is there's another force that's doing work in this situation. Yeah, exactly. Pretty much. The dog eating the homework. She's eating the homework before I can assign it. She's trying to sabotage us. We'll have to run her around a little or something and tire her out. Um, so yeah, if you hear some whining in the background, that's what's she's worked up right now for some reason. So anyway, there's another force that's also doing work. So the only other force that we have in our so why is the angle 0? So the angle is 0 because both the displacement and the holding force are pointing up. If you lift the cup straight up. Yeah, work. Like I mentioned, I mean the term work, it's one that just has a lot of baggage. It's kind of like force, right? Like we have a lot of kind of notions about things like work and force. And one of the things that's kind of cool about physics is these kind of common, humble sounding words actually have very precise definitions. So now we're talking about work. Well, now you know that work is actually the dot product between force and displacement. So why would force times distance equal mgd? Well, all I did was I substituted in here what the force was. So this is the holding force that I had mentioned. So I'm just putting that in here. That's where this is coming from. Yeah, those are excellent questions. So does that clarify that for you, Luke, as to what where that's coming from? So the other force that we want to make sure and keep track of is the force of gravity. And it's not I see. Yeah, it's not perpendicular. It is parallel, but it's actually anti-parallel to our displacement vector. So in this case, you can think of this in different ways. So gravity is also doing work, and now in terms of like this picture that I gave you of arrows, so our displacement is up, but our force of gravity is down. So one way to think about this is just that if you're going in the opposite direction, then the work is negative. So the work will be negative mgd. Actually, let me label these separately. So this is the work. Before we were talking about the work that I'm doing on the cup, and now we're talking about the work gravity is doing. So it's going to be negative mgd. Another way you can think about this is to say that the angle between them is actually 180 degrees. So then when you go and use your definition of FD cosine theta, cosine of pi, cosine of 180 degrees is what? What's the cosine of 180 degrees? You guys know this. Yeah, so this is another way conceptually to think about this is if the angle is very large, 180 degrees, then you'll pick up a factor of -1, and then you get the same thing. So this would be negative mgd. That can be a useful way to kind of keep track. Yeah, so when we get 0 with this situation is the situation that we mentioned above, where if your force here, let me put our example up here in terms of, so this situation when we moved sideways, but the force was up. So for this example, these are perpendicular. This would be FD cosine 90 degrees. In that situation, you know that cosine goes to 0 at 90 degrees, so this would be 0. That's the 0 case. No, it's totally fine. It's good to recognize those different cases. Think about the different cases. Okay, so that's basically this is basically the simplest work example that we can talk about because it's in one dimension. Let me give you a only slightly more, or are there any other questions with that before we proceed? Any questions? Other questions? Yeah, exactly. So that's where we're headed. What if the direction of movement is in an angle? Exactly. So let's look at an example kind of in that vein next. So the example that I want you to think of is, imagine you have a hiker and they're climbing up some hill, and they're carrying a bag, a backpack, a heavy pack or whatever, and the mass of this is going to be 15 kilograms. Okay, and we're gonna assume constant velocity, so we don't have to deal with this question of like, what about if it's accelerating? And basically what we want to do is, the questions that we're interested in, determine the work the hiker does on the bag, determine what gravity does, and determine the network. So net meaning total, like we had calculated net forces, right? Total force. So the network, the total work. Okay, so the first thing that we do, and I neglected to do this morning, and it threw us off balance a little bit. The first thing that we need to do is think about the forces. So the forces and the displacement that we have. So the displacement, oops, you can think of the displacement as the angle, or not the angle, but the diagonal here along the incline. The forces that we have are the force of gravity pointing down, and the force of the hiker is exerting on the bag, pushing it up. And again, we can sum the forces in y. So the hiker is pushing up, gravity is pulling down on the bag, and those are going to sum to 0 because the bag is not accelerating. And it may be helpful to question 1. Let's draw a picture of just the vectors, just so we can kind of keep ourselves oriented here. So the hiker's force is pointed up. The displacement is, along the incline. And so really, the angle that matters in this situation is the angle between them. We need this angle. We're so used to drawing angles like here, right? Well, for this question and for this discussion of work, this isn't necessarily the case. We actually want, in our picture, we want this angle. We want the angle between the force and the displacement directions. And then we can apply our definition for work. So work is F dot D, i.e. F D, cosine of the angle between them. Now, if we look at, and I should say this height is 10 meters. If we look at this D cosine theta, D cosine theta, i.e. the adjacent part of D, adjacent to the angle, that's going to be the vertical part, and that's another way of saying the height. So this D cosine theta is just the height. So in other words, this becomes the force of the hiker times the height. We can get the force of the hiker from the sum of the forces in the y direction. We know the force of the hiker is mg. So then this becomes mgh. So this is a little bit cheating. We didn't do a ton with the angle because we just looked at what the angle was in terms of another variable, but it gets in that direction, or it sort of you can see where this is going. That it's only the part of the displacement that's in the same direction of the force that matters. So in this case, the the D cosine theta is the height. So the work that the hiker does on the bag is given by just the amount that they have moved it up, and times the force that they're exerting on it. And notice a couple things. So this is in units. So we can actually let's put in the numbers just to talk about numbers. So the mass we said was 15 kilograms. G, of course, 9.8 meters per second squared, and then the height would be 10 meters. So this has units of kilograms meters squared per second squared, i.e. joules. If we multiply this together, you get 1470 joules. And there's no unit vector with this because this is a scalar quantity. It's just an amount of energy. Okay. So this is the work done by the hiker. So the next thing that we wanted to look at was determine the work that gravity does. Well, now our picture of the forces is flipped here in that mg is pointing down. So our angle, instead of it being this, it's this angle. The angle between them is so is it always positive? No, not necessarily. That's what we're getting to right now. So if the angle is bigger than 90 degrees, then you know that the F dot D is going to be negative. So in other words, like if we imagine, suppose the force was pointed along the x-axis, then basically anywhere over here would mean negative. And so in this case, the work FD cosine theta, now the force is now negative, so this becomes negative. D cosine theta, if we're thinking of this in terms of the height, it's not like the height has changed, right? So this, one way to think about this would be to say, okay, well this becomes negative mgd. Another way to think about this would be say, okay, well the angle now is gone from theta to 180 degrees minus theta. So if you look at it like this, like, if this was theta, and now we're talking about this, let's call it theta prime that's over here. We know that theta plus theta prime has to equal 180. So in other words, theta prime is 180 minus theta. And if you take the cosine of 180 minus theta, this is the same thing as negative cosine of theta. So that's another way to think about this, is that your mg, you could say mg is positive, and then pick up a negative h. Or the d cosine piece being negative, based on the angle being 180 minus theta. So there's different ways to think about this. I would say the main takeaway, though, is that the picture really helps you keep track of if it should be negative or positive. The picture really helps you keep track of your signs. Even just thinking about this stuff, I'm getting turned around, but I know that if I look at the picture, I can tell, oh, okay, if they're pointing in opposite directions, then I know that it'll be a negative. So this is the, let's see here. So the work done by the hiker. So if we look at the work done by gravity, it would be negative 1470 joules. And then the last question that we were looking, or subpart of this question was, well, what's the net work? And this is just the total. It's going to be, 1470 minus 1470 is 0. So the net work is 0. And we're going to relate this to something in a couple sections um, called kinetic energy. So this is a little bit of foreshadowing. But in this case, the net work done on the backpack is 0. Um, okay, so that's another example. It's not real detailed in terms of uh, actually evaluating the angle because we just used the fact that d cosine theta gives us the height, and then we put it in terms of the height. But we'll look at some questions tomorrow that actually have us look at different angles and we'll also look at a little more detail at the dot product. But that's where we're started. So you'll want to start reading chapter 7. And yeah, what questions do you have? Questions? Questions? Good. Not too complicated. Kind of get us started with a new concept. Work. Um, no questions? Well, I'm trying to be better about staying within our 50 minutes. So I don't know if people actually have anything at noon, but even so, um, so I will sign off here shortly if folks don't have any questions. Nothing? Well, I sure appreciate your patience, with this online all the time. It's definitely a little bit of a weird adventure. Yeah, so once you start digging into the homework, I'm sure some questions will pop up. We'll flesh out some more tools and look at a lot more complicated problems going forward. So um, cool. We will see you soon. So I'll either see you tomorrow in lab, or I'll post the lab later today, or see you on Wednesday. Alrighty. So have a nice day. We will see you tomorrow or Wednesday.